Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study about the deflection of beams. The course outcome on Bloom's taxonomy for this session is related to course outcome number 4. That is, apply the knowledge of theories of failure, shear force, and bending moment relations for analyzing the flexural stress, shear stress distributions, and failure of beam sections. Bloom's taxonomy level for this session is apply level. So what is the deflection of beam? Deflection of beam, here we can see in these figures. Figure A indicates simply supported beam. The type of beam is simply supported beam. At end supports, there are two supports are there, A and B, and midpoint C. It is the before loading, the beam position is a straight. And after the beam, after loading, at the point load W is applied, the beam will bend. This is called deflected. The beam will be deflected. So this deflection is known as the deflection of a beam after loading. It will bend. So if a beam carries a uniformly distributed load or uniformly varying load or a point load, the beam deflects. The beam is deflected from its original position. So in this chapter, we'll study the deflection of beams when it is subjected to uniformly distributed load, point loads, or cantilever or uniformly varying load, whatever the beam type of beam can be. So when those loads are acting on the beam, then the beam will be deflected from its initial position. So when the beam is deflected, it will be subjected to due to loads acting on the beam, and it will be subjected to bending moment. We have studied the radius of curvature, that is from the theory of pure bending, that is M over I equal to E by R and equal to sigma by Y. Where R is the radius of curvature, it remains constant if that from this relation, if you make it R equal to I times E by M. This I is second moment of area or moment of inertia of a section of the beam, and this E is the modulus of elasticity, and M is moment of resistance. The curvature, if it is R, it becomes constant. So the term E by M will be constant if the beam is subjected to a constant bending moment. This means that when a beam, when it is loaded, the beam is loaded, the value E by M becomes constant. And at that time, the beam will bend is a circular arc. So there are various types of beams. The various types of beams are here. Move on is cantilever beam. Another one is simply supported beam. Third one is fixed beam. And the fourth one is overhanging beam. So these are the various types of beams. And if you discuss about the types of loads, point load, and second one is uniformly distributed load, and the third one is uniformly varying load. These are the types of loads. Here it is a cantilever beam. It is initial position is straight. When the load is applied, when the point load is applied at the free end, it is bent into a deflection. It is deflected. That is, a deflection is denoted by delta. And this free end may be having certain slope. So in this chapter we will study the deflections and slopes of various beams when they are subjected to either point loads or uniformly distributed load or uniformly varying load or combination of these three. Now in the deflection of beams, here we can see the deflection and the slope of a beam having a uniform bending moment. The figure C consists of, here the beam is deflected. Initially the beam is deflected. After deflection, this is the ACB is the radius of curvature. And the supports at A and B, at ACB, and the supports are here at A and B is simply supported. The radius of curvature for this deflected curve, that is a deflected beam, is R is the radius of curvature of the deflected beam. The initial position of the beam is ACB, and after applying the load at the midpoint, the final position of the beam is AC-B. The length of the beam is L, and ACT equal to CB, that is L by 2, where Y is here, Y is the deflector. What is the Y? Deflection of the beam at the center, that is the distance of C to C dash, and I is the moment of inertia of the beam section, where E is Young's modulus for modulus of elasticity for the beam material, and here theta, this R is intersecting at O, this making angle theta, that theta is the slope of the beam at end A. This is also theta. If it is theta, normally the total is 90 degree, then this portion becomes 90 minus theta. If it is 90 minus theta, it is 90 degrees and it becomes theta. The angle of this theta is the slope at the end, left end A, made by the tangent we have drawn. One tangent, that is the tangent A at the tangent with the beam AB. So practically, this is the theoretical. The deflection is here, the visible or recognizable quantity here, parameter, the deflection. But practically, the Y is a very small quantity. It's very small in millimeters. Not in centimeters, in millimeters. It's very small quantity. The deflection is. So this is the description of the deflection of a slope and the deflection and the slope of a beam after deflection, after applying the load. Now here, if we consider the slope, if it is this theta is very small quantity, then tan theta equal to theta, but tan theta equal to the dy by dx in relation to that, in terms of deflection, that a dy elemental, that is dy and dx, dy by dx equal to tan theta, and this AC equal to CB, that is AC equal to BC, that equal to L by 2. Now also from the geometry of a circle, AC into CB, that equal to AC into CB equal to DC times CC dash, the factor from the concept of geometry of the circle, AC into CB, the product of the length, that AC into CB equal to DC into CC dash, the factor remains same. Now that is L by 2 times, what is the AC and CB? AC equal to CB equal to L by 2. Substitute here L by 2 and L by 2. What is the DC here? That DC means, that is the DC means DC equal to DO plus OC. So we know that DC equal to this DC, we want DC means that is the distance of DC dash minus CC dash. Here this term DC equal to DC dash minus CC dash. What is the DC dash? DC dash means 2R. That's 2 times R. CC dash means Y. 2 times RY minus Y. 2 times R minus Y. What is CC dash? The CC dash is the quantity of the Y. Now, L square by 4, after simplification, L square by 4 equal to 2R minus Y square. For a practical beam, the deflection Y is very small quantity. If the Y is very small quantity, what is the square of the Y? That becomes very small quantity, so it is negligible. Then after simplifying that equation, then L square by 4, that is L square by 4 equal to 2RY minus Y square. This Y square is very small quantity because Y is very small, so in practically, so Y square becomes small quantity, so this quantity is negligible. Then the term becomes L square by 4 equal to 2RY. Then Y equal to L square by 4 into 2 is 8. L square by 8R. So this L square by 8R considered as a equation 1. Then we know the bending equation. From bending equation, what is the pure bending equation? The pure bending equation is M over I equal to sigma by Y equal to E by R. Here the terms are related is that M over I and E by R from pure bending equation. Some pure bending equation we can extract what is R, that R equal to EI by M. This is the equation 2 and it is equation 1. Now substituting the value of R in equation 1. What is the equation 1? Substitute what is the R value? EI by M. Substitute in equation 1. Then Y equal to L square by 8 times EI by M. Then Y equal to ML square by 8 EI. This equation gives the deflection, the central deflection of a beam which bends in circular arc. We have calculated here what is the deflection. Y. This Y equal to ML square by 8 EI. We have calculated so far the deflection term. What is the deflection for this beam is that ML square by 8 EI. Where M is, what is the M for? Moment resistance or bending moment. Where L is the span of the beam and E is the modulus of elasticity of a material, of a beam of a material. Where I is second moment of area or moment of inertia of the section. If it is rectangular section, if I is the rectangular section, if I is the rectangular, I for rectangular section, is B d cube by 12. I for circular section, that is pi, if the d is the diameter. Alright. Now I for circular section is pi d for 624. I for rectangular section is B d cube by 12. Provided B is the width and D is the depth. B d cube by 12. This is the formula of our about neutral axis. If we need I for square section, then B equal to D. Substitute in this. Then about neutral axis, B equal to, that means D power 4 by 12. That means B d cube. That is D power 4 by 12. Where D is the depth. Y is the deflection for a beam. What type of beam here? It is simply supported beam where point load is acted on that at the midpoint. Now coming to the slope, from the triangle AOB, AC equal to CB. If we consider the triangle AOB, then what is the sine theta term here? Is the right angle triangle. The term that is ACO is the right angle triangle. Sine theta equal to opposite side by hypotenuse or diagonal side. The opposite side is AC, diagonal side is AO. AC by AO. What is the AC value? L by 2. What is the AO? That is R. That means L by 2R. Now the angle of the slope is very small, then sine theta, the value of the slope is small, then sine theta equal to theta, that is in radians. Then sine theta equal to theta, that is L by 2R. We know R value. What is that R here? E by M. Substitute R in this equation. Then L by 2 times EI by M. That is ML by 2EI. This is the slope equation. ML by 2 times EI. This equation theta gives the slope of the deflected beam at either A or at B. If you draw a tangent at B also, this is also slope. So this is the slope equation, that is ML times ML by 2EI. This is the slope calculated. This equation theta is ML by 2EI. Where, what is the M here? Again, M is the bending moment or moment resistance. L is length of the beam. Length of the beam. Where E is modulus of elasticity. Where E is modulus of elasticity. I, second moment of area or moment of inertia. Area moment of inertia. So what is the unit for bending moment? Newton millimeter. Length of the beam, millimeters. Modulus of elasticity, Newton per square millimeter. Moment of inertia, millimeter per 4. So this is the slope equation. This is the slope at deflected at B of a beam. Which beam? Here it is, simply supported beam at edge A or B. That is the slope theta. Slope is denoted by theta, and deflection is denoted by here deflection. Here deflection has taken place at the midpoint, maximum deflection, that is the Y, ML square by 8EI. So the unit for deflection Y is in millimeters, ML square by 8EI. Unit for deflection is millimeters. Okay, let me derive the deflection units from this equation, that is ML square by 8EI. Y equal to ML square by 8EI. Y equal to ML square by 8EI. Unit for M is Newton millimeters and L square is millimeter square. 8EI, E for Newton for square millimeter, I mm for 4. So what will happen here? Mm square 2 times, this 2 times mm square get cancelled, Newton got cancelled. Then unit for deflection is millimeters. Unit for deflection. What about unit for slope? The unit for slope is in radians. Slope comes in radians. Theta equal to ML by 2 times EI. Now sin theta equal to theta. Now next, we have to find out the relation between slope, deflection and radius of curvature. Slope, deflection and radius of curvature. Here there are the two figures are here, figure A and figure B. Now we consider the deflection curve. What we consider here, the deflection curve is AB. The AB is the deflection curve, AB. So the deflection curve AB represents, okay, of the beam here, the deflection curve of a beam AB. A small portion we considered. Actually, we have to find out, our objective is that what is the relation between slope, deflection and radius of curvature. Slope is theta, deflection y, and radius of curvature r. Theta y r, that is relationship we need here. From the considered the same curvature we considered AB. So we considered here the small portion, consider the small elemental portion PQ of the beam. And we have drawn a tangents at point P and point Q. Those tangents made angles with axis X, psi and psi plus del psi. These are the tangents we made. These are the tangents. And this is another tangent B with x-axis, that is psi plus d psi. So with the x-axis, so another thing, we have drawn a normal to these tangents at P and Q, then intersected at point C, at point O here. Yes, point C. These are the normal to the tangents intersected. The tangent at point C made angle between these two normals is d psi. Now the radius PC equal to QC, that equal to radius of curvature R. So this PQ portion is d psi, ds. So that is a description of figure A. Coming to the description of figure B, when these two tangents are making an angle psi and psi plus d psi, so by using the concepts of geometry, so the making angles here, if it is the psi, the intersection, the point, curvature making, this d psi, this is the d psi making an angle. This is the psi value with the PC is a PC normal is making with vertical, that is the psi, and the total with the and c plus psi plus del psi is make d psi is making the Q, making an angle with x-axis, that is psi plus d psi. These angles are same as these angles. Now difference between these two is the d psi is making. Now figure B description here. This, what is the point C name? The point C is known as the center of curvature of PQ, elemental radius, that is a ds. So the length of PQ is the ds, and the angle made PCQ, angle made PCQ equal to d psi. Then PQ equal to, then what happens? PQ equal to, what is the PQ? Thickness, that is the PQ is ds. So this is the ds and it is r. The angle is making d psi. Now ds equal to, from the concepts of geometry, that's r d psi. Then r equal to ds by d psi. But if x and y be the coordinates of P, then x and y be the coordinates of P, then what will happen here from the concepts? The dx and dy, from these concepts, this is a psi angle, d psi. Then what happens? Tan psi equal to, from this equation, from this triangle, this is the psi angle. This is the ds, hypotenuse, or diagonal side is ds, opposite side is dy, adjacent side is dx. Then tan psi equal to dy by dx. This is dy, is dx, it is dx, it is sin. Tan psi equal to dy by dx, sin psi equal to opposite side by diagonal side dy by ds, cos psi equal to adjacent side by diagonal side, that is dx by ds. These are the three relations. Then now the equation 1 r equal to ds by d psi, we are going to write in terms of dx, dy and ds. So that r equal to ds by d psi modified, we want in terms of cos psi and sin psi or tan psi. So ds by dx, both numerator and denominator divided with dx, ds by dx and d psi by dx. This ds by dx is known as, from the relation, ds by dx means inverse, that is 1 by cos psi, and d psi by dx same as d psi by dx. Do you know any term here d psi by dx? Yes, we don't have anything. Keep it as it is, that is r equal to 1 by cos psi means secant psi by d psi by dx. This is equation number 3. Now this equation number 2, what is the number 2 equation? That is tan psi equal to dy by dx. This tan psi can be written as 1 plus secant square psi. Or if you differentiate equation 2, that is tan psi equal to dy by dx, differentiate it with respect to x, then secant square psi d psi by dx equal to d square by dx square. Then d psi by dx equal to d square by dx square by secant square psi. Then we know the value of this. Now we got it, the value of d psi by dx. This substitute this d psi by dx in the equation 3, that is r equal to secant psi by d psi by dx. Substitute this term here, then r equal to secant psi by d square by dx square by secant square psi. Then it becomes secant square psi and secant psi and secant square psi by d square by dx square. Then secant psi and secant square psi, then it becomes secant cube psi by d square by dx square. Now, by taking the reciprocals from both sides, then 1 by r equal to d square by dx square by secant cube psi. Then 1 by r d square by dx square by secant cube psi. Here, for simplification, what we are doing here, secant square psi power 3 by 2 we made. So in such a way that we can substitute in the place of secant square psi is 1 plus tan square psi. So d square by dx square by 1 plus tan square psi power 3 by 2. That is 1 by r equal to. Finally, the secant square psi, then 1 plus tan square psi, the psi, tan psi at any point. The tan psi is very small quantity. The tan psi is a very small quantity. So that, okay, tan square psi is a very small quantity. So what we have done here it is, we neglected the tan square psi. The equation here it is 1 by r equal to d square by dx square by 1 plus tan square psi power 3 by 2. This tan square psi is small. Then tan square psi is small is neglected. Then 1 power 3 by 2 is nothing but 1. Then it becomes 1 by r equal to d square by dx square. Now from the bending equation we know m by I equal to E by R. So 1 by R equal to m by EI. Substitute in the place of 1 by R the term, the value, that is d square by dx square. So m by EI equal to d square by dx square. Then m equal to EI times d square by dx square. This is the equation, that is the moment resistance equation of the deflection, that is a equation, the moment resistance equation, that is EI times d square y by dx square. So this is relation between from this 1 by r, relation between the slope and deflection radius or curvature, but here is the moment resistance equation. If you differentiate with the once this one, that is d with respect to x, dm by dx equal to ei times dqy by dx cube. From the concepts of shear force and bending moment diagrams, this dm by dx is nothing but shear force. Then F equal to EI times dqy by dx cube. This F equal to EI times dqy by dx cube, this is the equation of shear force equation. And F equal to EI times d square y by dx square, the equation of moment of resistance equation. So now, differentiating this equation still further, then what will happen here? That is F equal to EI times dqy by dx cube. If you differentiate with respect to x, then it becomes df by dx times EI times d power 4 y by dx power 4. This df by dx is known as the rate of loading, small w. That is, w is the rate of the loading. Then w equal to EI times d power 4 y by dx power 4. Now, the slope equations. First, the deflection is y, denoted by y, and the slope is denoted with theta. The theta is deflection, derivation of deflection with respect to x becomes a slope, dy by dx. Now, what is the bending moment equation? Bending moment m equal to ei times d square y by dx square. If you differentiate this bending moment equation with respect to x, the shear force equation is observed, that is ei times dqy by dx cube. After differentiating the shear force with respect to x, we can observe the rate of loading, that is UDL, uniformly distribution load, that is ei times d power 4 y by dx power 4 y. So these are the equations interconnected with each other. First, begin with the deflection y. Differentiating deflection with respect to x comes to slope. So next, bending moment equation, it is in terms of bending moment equal to ei times d square y by dx square. This ei times d square by dx square, here the radius of curvature is involved, and dy by dx slope is involved, and y is the deflection involved. Now, differentiating the bending moment with respect to x, shear force is observed. The shear force equation is ei times dqy by dx cube, and the rate of loading, differentiating the shear force with respect to x, rate of loading, that is ei times d power 4 y by dx power 4 y, dx power 4. These are the interconnected relations between from deflection to slope, slope to bending moment to shear force, and shear force to rate of loading. This rate of loading comes into uniformly distributed load. So what are the units for E? Units for E: modulus of elasticity, that is Newton per square millimeter. I, it is millimeter per 4. Area moment of inertia. Y is the deflection, it is in millimeters. M is taken as that is bending moment, that is Newton millimeters. And finally, X is with respect to X is in millimeters. So these are the relations with respect to relation between slope, deflection, and radius of curvature. So in this section we have studied, let us recapitulate what we have discussed here. What is the deflection of beams? Concept, introduction we have studied, and deflection of beam, slope and deflection of a simply supported beam. Consider the point load is acting at the midpoint, and what is the slope and deflection equation. And also we have studied the relationship between slope, deflection, and radius of curvature. The slope and deflection, radius of curvature, in summary, here it is. This is the summary slide. Deflection with y, slope with theta, bending moment, shear force, and rate of loading we have studied in this session. And these are the references we have followed. References followed, textbooks and web references covered. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.